Hey everybody, in this next example we're gonna go over one that we did in class last time. So we are looking at the region bounded by the graph of y equals x squared, so the parabola, and the line y equals 9 in the first quadrant. So when we did this in class, and just to remind ourselves, we took a little rectangle, right? We chop up the region into tiny little rectangles, infinitely many, and then add them all up from, we're looking at the x-axis from where the region starts on the x-axis, so this starts at 0 to where the graphs intersect. So this is going to happen at 3. And you can, by looking at the graph, we can see that, or you can also set the equations equal to each other. 9 equals x squared, set it equal to 0, and solve. So we see that these graphs intersect when x is minus 3 and when x is 3. We're looking at just a shaded region, so this is in the first quadrant. So we're looking at x equals 3. So this is the point 3, 9. So when you draw yourself a little rectangle, what I want you to think about is how does that rectangle move? So it moves from left to right, starting at x equals 0. So you will have a bigger rectangle here, all the way to x equals 3. Tiny little rectangles as you get close to the 0.39. So the area for this particular region is the integral from 0 to 3 of the height of the rectangle times the base, right? The area of a rectangle is base times height. The base is dx and the height is top minus bottom. So in this case, we get 9 minus x squared dx. And we did this example in class, but I just want to integrate it fully. And so I'm going to have 9x minus x cubed over 3 from 0 to 3. And then plug in the 3. Always do top minus bottom. So it kind of makes sense, right? When you think about the height of the rectangle, we do top minus bottom. When you use the fundamental theorem of calculus, you use top minus bottom to evaluate the top limit minus the bottom limit. So in this case, we're going to have 9 times 3 minus 3 cubed over 3 minus, plug in the 0. 9 times 0 is 0, minus 0 cubed over 3 is 0. So in this case, it goes away, but it doesn't always go away. So here, what do we have? 9 times 3 is 27, minus 3 cubed is 27, divided by 3 is 9, and 27 minus 9 is 18. So that's the area, the shaded region. Now, the reason that I want to do this problem, even though it seems simple, is we're going to switch gears a little bit. So what if, instead of doing a rectangle that is vertical, so chopping up the x-axis, what if instead we cut up the y-axis? So we do our cross-sections horizontally. So we are taking cross-sections along the y-axis instead. So we're going to go all the way up here. So I have a horizontal rectangle. So what does that mean about this guy? So the area, this is still a rectangle, so the area is still base times height. But now our base, since our rectangle is kind of laying down, this is, instead of being delta x, is delta y, because we are taking cross sections along the y-axis. So think about like slicing the y-axis instead of the x-axis. So that gives us horizontal rectangles. Now, what is the height of that rectangle? I know I'm saying height and it looks horizontal, but imagine that it's vertical, or you can also think of maybe the length of the rectangle, right? If you're thinking about length times width. So the width is delta y, and what is the length? So the length in this case is that distance. So is this function minus the other function. So kind of like we did here, top minus bottom for the red rectangle. Now it's going to be the length from the y-axis. So another way you can think of it is that this is going to be the right function minus the left function. So the parabola is the right function, and the y-axis is the left function. And so when I set up my integral, the area is going to be, now notice that our rectangles are moving horizontally, starting from 0. Or sorry, our rectangles are horizontal, they're moving vertically. Starting at 0, you're changing the rectangles all the way to where? We're going to stop when y equals 9. So our integral is going to go from 0 to 9 in the area of that little rectangle. And so the area is length times width. So the length is the right function minus the left function, and dy is the width. And notice that there's something going to go, it's not going to go so well over here. The right function is y equals x squared. So I have x squared minus the y-axis. And there's something amiss here, right? Because we have dy. It's like, wait, we can't have x's and y's. So that's because this is not okay. So we need to write in terms of y. So we want to write this in terms of y, since we have a dy integral. So going back to our function, I know that y is equal to x squared. So what does that mean about x? X is equal to plus or minus the square root of y. And I'm looking at the right side of the parabola, so it's going to be the positive one that we're going to take. So our area then is actually the integral from 0 to 9 of the square root of y minus 0 dy. So from 0 to 9, the square root of y dy. Right, so notice that now our equation is x equals the square root of y here. In the equation, remember we talked about the equation of the y-axis is the line x equals 0. So let me write that over here. The y-axis has equation x equals 0, a vertical line. And so that's why we end up with this. And so it's representing the same area, it's the same region, it's just a different way of doing the integral. So doing it the first way, we got that the area is 18. Should we get a different number? No, right? We should get the exact same thing, it's the exact same area. So let's integrate it. So in order to integrate it, we're going to rewrite it so we can use the general power rule. And the antiderivative of y to the 1/2 is add 1, so it's y to the 3/2 divided by 3/2 is the same thing as multiplying by 2/3 from 0 to 9. And plug in always the top limit first, so 2/3 9 to the 3/2 minus 2/3 0 to the 3/2. This one is 0. So we're just left with 2/3 times, think about how do we do rational exponents. So this is really the square root of 9, that's the half, and then cube, the 3. The square root of 9 is 3, so we end up with 2/3 times square root of 9 is 3 cubed times 27. So we are left with 2 times 9, which is 18. So we get the exact same value. So two ways of doing the area. So we can do it as a dx integral. A dx integral means we have a vertical rectangle as our cross section, or we can do the area as a dy integral. Dy integral means we have a horizontal cross section rectangle. So when is this helpful? Let's do an example of why we might want to do a dy integral. Okay, so let's try this example of benefits of why a dy integral is helpful. So find the area of the shaded region. So we have 3 lines, y equals x, y equals 2x, and y equals 6. So the region bounded by those 3 graphs. So now notice that if I want to find the area of this region, we'll do it as a dx integral and as a dy integral so we can see the difference. Okay, so when you think dx integral, what I want you to picture is vertical rectangles. You have a vertical cross section. So we're chopping up the x-axis. So I'm going to have rectangles that go up and down. And so the question is top minus bottom obvious? So if you start drawing yourself little rectangles, I see, okay, yeah, top minus bottom is, I'm going to have 2x minus x, 2x minus x. But then what happens? Notice that when I draw a little rectangle up here, did top minus bottom change? Yes. Now notice that for one of the rectangles in this region of the triangle piece, the top function is 2x, the line y equals 2x, and the bottom function is the line y equals x. So top minus bottom is 2x minus x, whereas any rectangles in this region, the top function is y equals 6, so it will be 6 minus x. So that means that I'm going to need two integrals, and the split point happens here. So I need to find what is this point of intersection where I need to split my integrals. So that happens when 2x equals 6, which means when x is 3. So I'm going to split them at x equals 3. And this is y equals 6 and y equals x, so these is x equals 6 as well. So I'm going to have the area is equal to the integral then from 0 to 3 of top minus bottom. So top minus bottom, it will be 2x minus x dx. Right, plus I need the other integral, the integral from 3 to 6. Why do I need two integrals? Because top minus bottom change. Now the top function is 6 instead of 2x. So it will be 6 minus x dx. And we can integrate it. So this is the integral from 0 to 3 of 2x minus x is just x dx, plus the integral from 3 to 6 of 6 minus x dx. So this is x squared over 2 from 0 to 3 plus 6x minus x squared over 2 from 3 to 6. And so we can evaluate this very fast. So I'm going to have what, 9 halves plus, when you plug in 0, that goes away. So plus this one. So 6 times 6. So I'm going to have 36 minus 36 over 2. So that's 18. And then plug in the 3. Minus 6 times 3, which is 18, minus 3 squared over 2. So 9 over 2. And so notice that here, when we do this, I'm going to get 36 minus 18 again. So 36 minus 36. So those cancel. But this minus times that minus gives us a plus. So I'm going to end up with 9 halves plus 9 halves, which is 18 halves, which is just 9. So that will be the area of the region here as a dx integral. So now let's try it as a dy integral. Right? So in this case, I had to use two integrals. What happens when we do it as a dy integral? So let's look at the same region. So as a dy integral means horizontal cross sections. So horizontal rectangles. So when I do a horizontal rectangle, remember the height or the width or the length, sorry, the length of a horizontal rectangle is right minus left. So as we did in the previous one, I asked you, does top minus bottom change? Top minus bottom, top minus bottom. Well, yep. After that blue line, the top function changed from being 2x to being 6. So that lets me know that I need two different integrals. So for this one, does right minus left change? So as I move this little rectangle, the horizontal rectangle up and down, are either my right function or my left function changing? And it's not, right? So in this case, as a dy integral, we only need one integral, whereas for a dx integral, we needed two. So in this case, I would choose to use a dy integral because I don't have to split anything up. So the area is going to be the integral from, now these need to be y values. As before, the other one was moving left to right, so you use x values. This one is moving up and down, so we use y values. So this goes from 0 to 6. They happen to be the same just because of our y equals x line. So the area is the integral from 0 to 6 of, because I'm going to have a dy integral, I need to have right minus left. And because I have dy, what does that mean about these functions? They need to be in terms of y. So let me go back over to the functions and usually solve for x to get in terms of y. This is already y equals x. Here I have y is equal to 2x, which means that x is equal to y over 2. So when I do right minus left, looking at this, what's the right function? The right function is x equals y, and the left function is x equals y over 2. So when I do right minus left, those are the functions we're going to use. So a is equal to the integral from 0 to 6 of the right function, so y, minus the left function, y over 2 dy. Only one integral needed. Now, before our answer was 9, so let's make sure that we get the same answer since it's representing the same region. So I'm going to get y squared over 2 minus, oh, I guess I should have simplified this. We can combine like terms to make it better. So this is integral from 0 to 6 of just y over 2 dy, right? Y minus y over 2 is y over 2. So I get y equals, or a equals y squared over 4 from 0 to 6. And 6 squared is 36, so I get 36 over 4, which is 9. So we get the exact same answer. But what would you rather do? Would you rather do just one integral or have to split it up into two different integrals? So that is one of the benefits of using a dy integral versus a dx integral. Another benefit, and we'll talk about that in class, is that sometimes when you set up something as a dx integral, it may be that we can't integrate it because we don't know the method of integration yet. We haven't learned it. So we may have to switch it to a dy integral so that we are able to integrate it. But we will talk about that in class. Email me if you have any questions.